Welcome back to our series on electricity and magnetism. In this episode, we're going to apply Gauss's law to two particular geometries. The first will be a linear geometry. And this is a problem that we actually solved by looking at integrating a charge distribution. Well, we're going to try it a second way, and you'll notice that this is considerably easier. This is going to involve some assumptions, though, and we'll talk about those as we arrive there. Okay, there is our line of charge. This is assumed to be very, very long, so long that we don't have to worry about what are called the edge effects. So you can think of it as infinite. In essence, we'll have a lambda here. That is, we will have a charge distribution of a ratio of charge per unit length. That means because it's infinitely long, it really contains infinite amount of charge, but we're only going to consider a fixed length of it, because if we look at the field there, the field will be uniform all the way along. Okay, our first goal then is to exploit the geometry and construct a Gaussian surface. Keeping in mind that what our goal is to make sure the Gaussian surface meets all of the field lines perpendicularly, so that the normal vector for the surface is parallel to the electric field lines. Well, if the charge is uniformly distributed along this line, then those field lines exclusively go up, down, they come out of the board, they come into the board. In essence, it's like a cylindrical shaped field that gets stronger as we go towards the line and gets weaker as we move away. There aren't any field lines that point diagonally because they would all cancel out. Each little element would produce a spray of electric field, but of course the element right next to it would produce the same spray, and the one next to it the same spray. So all the components that pointed along the line would cancel, and only the components that point perpendicular to the line survive. So for an electric field shape for a linear distribution, the shape of the field, as long as the charge is distributed uniformly, is outward. It's not a uniform field. It does grow weaker with radius. So our correct Gaussian surface will be a cylinder. It will be a cylinder that wraps around the wire, keeping the same radius from the wire all along its length. So it will have two caps at each end, together with a cylindrical surface that joins them. And we're going to say that the length of it from center to center is L. So L will represent how tall the cylinder is. Now this works as a Gaussian surface because all the field lines then pierce the surface. And because we're assuming this is long enough that we don't have to worry about the edge effect, no electric field pierces either of the end caps. So the only place we have to worry about field is on the actual surface. That's the only place where flux is going to occur, is in the band that's wrapped around the sides. So let's write Gauss's law and then see about substituting in the appropriate elements. So first, Gauss's law, the closed loop integral of E dotted with dA is equal to the total charge enclosed divided by the permittivity of free space. In the previous video, we actually derived that using a point charge, but it applies to any charge distribution. As a matter of fact, it applies to any enclosed charge by any Gaussian surface. Unfortunately, with a lack of symmetry, this integral would be difficult to perform. But in this case, because we've chosen well, we've chosen a Gaussian surface that matches the geometry, notice that at every point on the surface of the sphere outside of the end caps, the electric field is constant. There is no electric field on the surface of the end caps at all because the field exclusively goes outward. That means E can come outside of this integral, and we're simply left with the electric field magnitude times the closed loop integral of dA. And then that's going to be equal to Q enclosed over E naught. Well, I still have two things to fill in. I have to fill in the enclosed charge, and I have to fill in the integral of the area. Fortunately, it's a cylinder whose dimensions I have defined. This cylinder has a radius of capital R. That's also the distance away where we're actually interested in calculating the electric field. This is the electric field we're interested in. And further, the enclosed charge, because this has a length of L that's actually inside the Gaussian surface. then L times lambda will be equal to Q. The entire charged enclosed will just be L lambda. Let's make those two substitutions. First, what's the surface area of the side of a cylinder? And of course, that's equal to the circumference of the end cap, 2 pi r, times the length of the side. So it's E times 2 pi r times L, and that will equal the enclosed charge, which is lambda L, divided by E naught. And you can see our final step here is the instrumental one. I can find the electric field at a distance r away from the wire by simply dividing out everything on the left side outside of E. Now, some of this cancels the L's on each side, which I knew it would be. After all, we can't have the length of this cylinder be part of the electric field formula because the cylinder was a construct. It was only placed in order for us to solve the problem. It has no real meaning like the radius does. So E for the electric field at the surface of the Gaussian cylinder is equal to lambda, which again represents the charge and the charge distribution, divided by 2 pi E naught times r, the radius. That is how far away we are from the wire. So this is a much easier way to find the electric field than integrating along the length of the line, taking all the little dq's and the geometry of the radius and integrating k dq over r squared. Now, unfortunately, it only works because we can exploit the symmetry in utilizing Gauss's law. But that's the real power of Gauss's law, is the way that it takes what would otherwise be a complex problem and makes it relatively simple. This is the electric field for a very, very long straight wire. All you need to know is what is the charge density and how far away from the wire do you want the electric field, and there it is. Now, we'll do an exercise where we will also compare this to the electric field we get from this wire by actually integrating along its length. It will be a considerably more difficult problem, but we will see that the solutions, they compare favorably. So if I have my choice, I'd prefer a Gauss's law solution to this problem. Okay, let's apply Gauss's law then to a second geometry. This geometry is going to be a flat sheet of charge. We're going to basically take a flat plane, and I'm going to uniformly distribute a charge all across its surface. Because this is not a linear charge distribution, this is instead a planar charge distribution, I'll need to use a different variable. This will be sigma, the area charge distribution, and as a ratio that will equal the total charge divided by the area. Once again, just as we did with the linear charge, I sort of assumed this was so long that we didn't have to worry about the edge effect. Wherever we drew our Gaussian cylinder, I didn't have to worry about field leaking through the edges, because that would have made this integral impossible to evaluate. We would have needed to know how much electric field leaked through the edges, what its angle was, and how it related to the area. We'll do the same thing here. We'll invent a very pleasant fiction, and that is, this plane is so large that the edge effect of the electric field lines deviating as they get near the edge, we don't have to worry about that. The electric field lines everywhere in the plane then point either straight up or straight down, and they always remain perpendicular to the plane. And that gives you a clue as to how we're going to draw our Gaussian surface. The Gaussian surface in this case is unusual. I call it the cookie cutter model because we're going to think of this plane as rolled out cookie dough, and we're going to use a cookie cutter to carve a piece of it out. I'm going to use a round cookie cutter that has a round top surface, and then it goes down until it runs right into the plane itself. And this is where the dashed line is, where it's actually carved through the plane. And then it continues through to the other side to the same depth. Basically, it has to be the same distance on either side, and anywhere on this surface is where I'm interested in calculating the electric field from that. That way I can make this cookie cutter as tall or as short as I want to, so I can get to any distance away from the surface of the plane that I want to. Just like I did over here by controlling the radius of the cylinder in order to control where I wanted the electric field, I can simply control the height of the cylinder. Now notice, because all the field lines exclusively go up or down, They will only pass through the end caps. They don't pass through the sides, and so I don't have to worry about those portions of my Gaussian surface. The reason why is there's no flux passing through them, so there's no contribution to the electric field. All I have to deal with is the top cap and the bottom cap, because electric field goes in both directions. So there'll be two parts to the Gaussian surface, the top area and the bottom. Just for the sake of argument, I'm going to need this area possibly, so let's call this r, and that's the radius of the top Gaussian surface, and I'll call this distance here d, and that's how tall it is going above. Again, it goes the same distance down below. Okay, well, we should now be ready to write out Gauss's law and to solve for the electric field at a distance d from a uniform plane of charge. Once again, I'll write Gauss's law, the closed loop integral of E dot dA, and that equals the charge enclosed divided by E naught. Well, in this case, what I need to do is fill in the area and pull out the electric field. You'll start to notice a pattern where Gauss's law's application is pretty much identical every time. The Gaussian surface may change shape, but the mechanism is the same. Because I chose my Gaussian surface as well, the electric field is always perpendicular to the surface, and therefore it's not a function of area, so I can simply pull it out. So it will be the electric field times the closed loop integral of dA, and that will equal the enclosed charge over E naught. Well, I want to fill in both the enclosed charge and this surface area. The surface area is easy. It's the circular cap on the top and the bottom. They both have flux going through them, so they're both part of the area that's encountered here. The top one has an area of pi r squared, as does the bottom. So we will say that it's E times 2 pi r squared. The 2 is because there's a top cap and a bottom cap. Okay, how about the Q enclosed? Well, it carved out a shape of charge that's exactly the same shape as the cross-sectional profile of the cylinder. That's why I call it the cookie cutter model, because it cuts out a cookie of charge that's exactly the same shape as the Gaussian surface I selected, in this case a cylinder. So that would be, the Q would be sigma times the area of that little region, and of course that area is also pi r squared. So it would be sigma times pi r squared. And of course that's still divided by E naught. Okay, and then now we're ready to solve for the electric field. There's an r square on each side and a pi on each side, so they cancel out. And you'll see that the electric field, due to a uniform plane of charge, is equal to sigma divided by 2 E naught. And that means the magnitude of the electric field is no longer a function of radius. As I move further up and further down, and I change how large this Gaussian cylinder is that basically carves out the portion of charge, I don't experience any decline in the size of the electric field. And that, of course, is because these field lines are all parallel. They experience no loss of intensity over distance. When it was a line of charge, they are inversely proportional to the radius. That's right here. And that tells me that the intensity of the field line decreases as I move away. That's because those field lines will definitely deviate, and therefore they'll be further apart with a lower density at distance. But not so with a plane. A plane of charge produces a uniform electric field above and below the plane. Again, taking into account that we kind of cheated a little because we had to express the idea that this field is so far from the edges that the edge effect has no impact on our analysis. So there are two applications of Gauss's law. What I would say would be the two easiest applications, and that is using a cylinder for a linear charge distribution and using a cookie cutter for a planar charge distribution. We will go one step further, and in our next video, we will look at spherical distributions, and we'll start to look at the difference in the ways in which conductors and insulators operate, especially when they're shelled, when there are consecutive cylinders or spheres that have different charge in them, and how conductors and insulators will respond to them. So that'll be the content of our next video.